Thank you, Luke. Today, I'm going to share with you our recent work on data analysis and the modeling of land-atmosphere interactions. This is based on our ongoing work by group members Michael, Jack, and Josh. Many of us are involved in model evaluation and improvement, and we all recognize that model evaluation needs to go beyond the simple use of an individual variable such as precipitation to include relationships, because the use of relationships would provide the necessary insight for model improvement. The challenges are, first, what's the right approach to evaluate and determine the appropriate observation-based data sets for relationships? When we talk about the individual variable, for example, for precipitation over the Amazon, we really don't know which product is the best. What people typically do is to use the multi-product ensemble average as the quote-unquote ground truth, and then use the standard deviation among the different products as the uncertainty. The question is this approach appropriate when we talk about relationships? Turns out it's not appropriate. So we need to find the right approach. Once we have the right data sets, then we need to decide what are the observed relationships. This is a broad challenge and a broad topic. Here, I just try to illustrate our approach in addressing these challenges using 3 examples. You might wonder, why do I pick up 3 unrelated topics? Well, in my group, everybody is doing the exploration or fishing every day, and until we find some exciting results, then we stop to write papers. So the point is, we start from land-atmosphere interaction, but that evolves into different topics. That's why I'm talking about 3 different topics, and we are writing 3 papers right now. If I don't have enough time, I might just cover the first 2 topics. The first topic is about the surface water balance over the Amazon River Basin. Well, we pick up Amazon for tons of reasons, and because it's simply important. For example, DOE has launched the Go Amazon campaign a few years ago. And for us, there is additional motivation. Last year, we published a paper on the E3SM ocean barrier layer evaluation. And the barrier layer is caused due to the ocean salinity. And as a part of writing that paper, here we show some results. Top shows the ocean-only results for the ocean-only modeling. And here the discharge is specified from observations. It turns out for the ocean-only modeling, there is a large bias in the ocean barrier layer at the mouth of the Amazon River. In contrast, in the fully coupled E3SM results in the bottom, the bias is much smaller. And of course, the question is this just an ocean model problem or an issue with observations used in the forcing? So when we talk about the model evaluation and development, we have to address this model versus data. At the same time, of course, we have done the evaluation of precipitation and runoff over the Amazon Basin, and here we also show the results over the Congo Basin. Top panel shows the results for the precipitation, and the bottom panel shows the discharge results. And the point is, you see the different biases in precipitation and in discharge. Again, are these just atmosphere and land model problems or issues with the observations, or both? For that reason, we have to look at the terrestrial water balance. Here, we take Amazon as an example. I write down the water balance equation: precipitation minus evaporation minus runoff or discharge equals total storage change for the land We can also write down the corresponding equation for the atmosphere would be precipitation minus evaporation minus divergence of water vapor equals total water vapor storage change. And our approach here is to test the water budget closure for different combinations of individual data sets over the Amazon River basin. So instead of testing individual variable, we test the combinations of individual data sets. Furthermore, because we work on the interface process in the Earth system, so instead of just focus on terrestrial side of the water cycle, we also use ocean salinity to innovatively as an independent consistency check of our results. And we include multiple data sets for each variable. 4 data sets for precipitation, 3 for evaporation, 2 for water vapor convergence in the atmosphere, and 3 for terrestrial water storage. And there is only 1 river discharge measurement at a specific station, but we also use the dietol method to upscale gauging station data to the river mouth. And the total number of closure combinations would be 30 plus. There are 3 ensemble means. There are also 3 salinity data from SMARS, SMAP, and Aquarius satellite measurements. And this figure summarizes some of the results. First, we can see those bluish colors shows the GRACE total storage data. Here we show the JPL retrieval and the solid line and the 3 product ensemble average dashed line. And the 3 GRACE data agree with each other very well in terms of the seasonal cycle. Next, we look at the golden lines. Here we show 3 lines. One is the residual based on using the era 5 precipitation, evaporation, and JPL total storage. And the residual is close to 0. In contrast, if we use the ensemble average of different products, the residual would be the dashed line or dotted line. Results are pretty bad. They are far away from closed. In other words, residuals vary substantially. And era 5, P and E give smallest residuals. And then next, we look at the top lines. And this line represents P minus E from era 5. Well, this dotted line shows the ensemble average P minus E. We see large differences. Furthermore, even though I'm not showing figure here, the large P minus E differences come from both P and E. And I also want to mention, not shown here, 3 salinity data sets have very similar seasonal cycles, even though their absolute values differ. And now we try to address the question, can we close the water budget? And here in this figure left panel, for the Amazon River Basin, we show all combinations. And the interesting thing is, for the combination based on the era 5, PE, and JPL total storage, we see the smallest residual within the uncertainty range. In contrast, if we use the all product ensemble, the data point is this one, deviate pretty far away from the full closure. So the point is ensemble means do not close the budgets. Furthermore, I want to point out at the bottom panel, there is a direct measurements of discharge at the red dot, that's the orbitals gauge station with the corresponding catchments or the river basin. And this would cover about 78% of the area of the entire Amazon basin. In contrast, for the whole Amazon basin, we also have to compute the discharge for the ocean model. And traditionally, people use the dietol approach, that is, by multiply the observed the discharge of the orbitals by a factor 1.25. if we use the direct measurements at orbitals, and then again the results from the area 5, P and E give the smallest closure error. And in contrast, the multi-product ensemble would not close the water budget. And furthermore, because the closure is even better based on the direct measurements of the orbitals, then based on the estimated discharge of the Amazon using this simple equation, this implies that the dietary method may not give the correct seasonal cycle, even though the climatology might be fine. Next, we can also use the ocean salinity measurements at the mouth of the Amazon River basin as a consistency check. Here, we are computing the correlation between different quantities versus the observed salinity. And again, we see the area 5 precipitation, evaporation, and JPL total storage together give the best correlation, almost -1. We expect negative correlations because more freshwater discharge means lower salinity. In contrast, if we use the observation of discharge from orbitals itself, the correlation is only -0.75. Again, indicates using a constant factor to convert orbitals discharge to the whole Amazon River discharge may not be very appropriate. Now, even though we talk about land-atmosphere interaction, we always have a view on the whole Earth system. So a straightforward application of our work is about the salinity in the ocean, the so-called the Amazon plume. And here we show the correlation between ocean salinity and the Amazon River discharge for different products, for the orbitals measurements, for the derived discharge based on the GPCP precipitation, area 5 evaporation, JPL total storage change, or the area 5 precipitation, evaporation, and JPL total storage change. And we see very different Amazon plumes over the Atlantic Ocean. This further demonstrates, even when we talk about ocean modeling, we have to pay more attention to the land-atmosphere interaction, for this case, the Amazon River discharge. Now, let me move on to a different topic, the snow water equivalence over canals. And we all agree snowpack is a major component in land-atmosphere interactions, and over Western US is also a major source for water resources. For that reason, lots of papers have been published on the data analysis and the modeling of snowpack over canals. The challenge is all the global data sets are pretty bad. Here we talk about the real analysis data, non-data simulation product, satellite passive microwave global data sets. Because people recognize the deficiencies of those data, then the usual way again is to use merged products of those individual products with the secret hope the merged product would be better. But turns out the merged products are also pretty bad. And how do we meet this challenge globally? I mean, well, that's why NASA has a plan for a new satellite mission to measure SWE in the future. But in the meantime, we came up with the idea to develop the high quality data set over canals, conterminous US. We actually spent 3 years to develop the UA daily 4 kilometer SWE and snow depth data set over canals from October 1981 to present, both for data analysis and equally important for model evaluations. And the input of our data are from the snowtail, sway, and snow depth sites, and in the middle panel indicated by the white squares and triangles in California, along with tens of thousands of NWS co-op snow depth sites indicated by those black dots. We also use the PRISM daily 4-kilometer precipitation and temperature data. There are two innovative ideas in our efforts. One is we find a very good, really terrific approach for the point area interpolation or extrapolation. And we also develop a new snow density model specifically for our data simulation because we need to combine swing measurements of the snow tail sites and snow depth measurements of the co-op sites. More importantly, we have passed 4 rigorous tests: point to point, point to pixel, independent evaluation using the airborne LiDAR data, and the evaluation using the independent of snow cover data, because snow cover is much easier to measure from space due to the substantially different reflectance from snow versus non-snow surface. Most importantly, we have passed independent tests by different groups. Here I just show the results from a completely different group. They just published a paper last December using the 40-year airborne gamma radiation sway record to evaluate the remote sensing product, that's the top panel SSMIS, and the merged product, that's global snow, widely used by many modeling groups. And of course, compared with our US product. The agreement between the US and their own measurements are so good, they concluded in abstract that US has much better agreement with gamma sway in all land cover types and snow classes, and the results demonstrate the reliability of the US product. Honestly, you cannot get a better endorsement than such a strong language. The actual good news is good for us, is also good for their own measurements using the gamma measurements method. In contrast, as an example, if you look at the results for evergreen needle-leaf forest, results from passive microwave are pretty bad, and the multi-product merged products also pretty bad. I'm not going to talk about any results in our own data analysis. Instead, I just try to answer one question because many modeling groups using the snowtail data for model evaluations. The question is, do point measurements of the snowtail sites represent the snowpack decline across the whole Western US? From observations alone, you cannot address this question, but with our gridded data, we can. What we have done is to compute the median trends using snowtail sites and collocated 4-kilometer grids, and they agree with each other very well, -2.8 and -2.9. Next, we compute the corresponding value using all 4-kilometer grids over Western US above 5,000 feet, because all those snowtail sites are above 5,000 feet, and the results are very different. The point here is that we do need to use our 4-kilometer gridded data for model evaluations. And that's indeed the case, what we are doing right now. Top panel shows the UA March sway climatology, and the bottom panel shows the March sway biases from 4 American models. Here I want to emphasize, we look at the EMIP runs of 4 American CMIP6 models, E3SM, CESM2, GFDL, CM4, and GIS model E2.1. The overall impression is that turns out E3SM simulates sway slightly better over corners than other 3 models, and the CESM2 produces too much sway over corners. And next, here we show the March sway trend. Top panel shows the results from UA, the bottom 2 panels from E3SM and GFDL model. The overall impression is both models miss the observed sweet trend near the west coast. So we don't see Sierra Nevada basically in the models. The challenge, of course, how do we gain any insights on models' performance? Then we can talk about the model improvements. And one idea we have explored is to compute the correlation between SWE and the temperature for left panels, SWE and precipitation middle panels, and SWE versus T and P for right panels. We can draw many points here. I just try to highlight 3 as indicated at the bottom. For observations, SWE has a strong correlation with P, particularly over Rocky Mountains, as indicated here, and has a weak correlation with T. In contrast, for E3SM, SWE has a weak correlation with P and has a stronger correlation with T. Finally, for observations and models, using T and P always yields much higher correlation than using T or P alone. Furthermore, we can look at the temperature sensitivity. Here, we represent by the coefficient multiplied by the standard deviation. In other words, we look at the coefficient for normalized temperature by its standard deviation and normalized precipitation, normalized by the standard deviation. And here we can see clearly for observations, as I said earlier, the sensitivity to precipitation, particularly over the mountains, is much higher than that of the temperature. And the second, the model on precipitation sensitivity is less than observed precipitation sensitivity. And finally, both models miss greater sensitivity to T and P over coastal mountains. And so far, we are talking about AMIP runs. And we have also done the comparison for the left panels from CMIP 6 coupled runs for the same periods, and the right panels for the AMIP type runs. And here we see different results between AMIP versus coupled runs. We actually see opposite results in terms of trends of the high Rocky Mountains for the E3SM and also for GFDL, they have different signs. Well, I don't have much time, so I will skip the third topic. Go to the conclusions. For the surface water balance over the Amazon basin, the first key point is the usual approach of using ensemble mean individual variables such as precipitation and evaporation do not close the water balance is not a good idea. Our approach of selecting combinations of data sets give us better approach to use the observational data sets for current and future model evaluations. Second, using the scaled albedo discharge to represent the whole Amazon discharge appears to give correct long-term mean but incorrect seasonal cycle. This has direct impact on the ocean salinity simulation. And the third point is again linked to the ocean salinity simulation. For the SWE over CONUS, again, we have developed a high quality data set over CONUS. The data set is available along with the metadata at the Oak Ridge Data Center. And the observed SWE shows more sensitivity to P than T. In contrast, models including E3SM show more sensitivity to T than P. This has implications on future SWE projection. I will stop here.